topic. Today we are talking about discovering machine learning. This is a beginner's guide, and I hope that with today's presentation, you have a little bit of an idea of what machine learning is all about. If you haven't done any work on it and you're wondering what is all this stuff about, what are we talking about, I hope that after this presentation, you'll be able to feel confident that you understand the concept. So I'm hoping that I can pack this in a format that is simple enough to get you started. But of course, there's a lot more to cover. So let's get going. So welcome today. My name is Oscar Garcia, and I'm a software engineer, like many of you. I develop on cloud, web, and AI technologies. I love sharing what I learn. I talk about my experiences. And if you're interested, I published a book called Data Engineering Process Fundamentals. I go more in detail about the data engineering process, because one of the things that you may not be aware of, for AI to work, you do need a lot of data engineering behind it. So you can scan that QR code right there. That will take you to a page that I have with links to GitHub repos and other good information that you can follow. I posted a GitHub repo link on the chat. Please, you can follow that. Please start the project, and I appreciate that. So let's get going. So what is machine learning? So machine learning is a subset of AI that has a focus on enabling computers to learn and improve based on a specific task, right? So the way it works really is not something that we actually program, but actually something that we let it learn based on data. So the idea is to have machine learning trained on lots of data, so it understands data patterns and is able to make predictions on those patterns. This is a lot different than, for example, when we used to program in a way that we used to do coding, and we used to say, I want to add this logic, and we used to do a lot of if statements and a lot of logic to be able to make our software smart. That's not the case here. Machine learning actually uses data, which makes it scale a lot more than just having someone or programmers just code it. So now you have many layers, right? You have artificial intelligence that has a lot of areas, right? But machine learning is actually focusing on data pattern recognition and learning. And behind that, also deeper into that, you have deep learning. If you heard about deep learning, which is another subset of machine learning that uses what's called neural networks. And neural networks is a whole different topic. It's more advanced. But just be aware that exists. All right. So why is it important? Well, what is the pattern here that we're trying to solve, right? So because machine learning now impacts the way computers solve problems, right? So like I said before, traditional systems used to program, right? So if you see here, like on your left, you'll see the old-fashioned code, if statements, if a person is over 50 and is overweight and diabetic, then that person has high risk for cancer. And those were a set of rules that we sort of established, and we used to program it that way. But with machine learning, that's not the way we do it. With machine learning, what we do is we just get this whole data set of medical information, right? So we have medical records from millions of people that are actually telling us that they have heart disease, they have diabetes, they're overweight, they're depending on the age, right? So they have all this stuff. So now with machine learning, we can feed that data into the model, into the training model, and then it will learn from that data and from those patterns. We'll be able to recognize patterns that will dictate whether that person has a high risk for heart disease, for cancer, and for other things, right? So for example, let's take a look quickly what I'm talking about here. So pretty quickly, when you go to this, just let me show you back here. You want to take a look at this repo here, machine learning, and I have a bunch of information here. I have introduction, I talk about regression, classification, deep learning, all those different things, right? And this is kind of very foundational. It just goes and shows you the concepts and everything that everything that the machine learning is all about, with a lot of codes, right? So a lot of codes. So you will see in every one of these folders, you will see a README file with some Python notebooks or Jupyter notebooks, and that's where the code is for this. So as you get a chance, you can take a look at that, and at your leisure, you can actually use it, work on it, and play with it. So what we're gonna do right now, pretty quickly, we're just gonna dive into the code right away, and we're gonna go to the introduction. Right, introduction. You can read the README file back into deeper details of what is machine learning, core concepts, and all of that. But here, what we want to really look at is we want to take a look at this comparison. Jupyter notebook file, if you're familiar with it, is just a way to really run Python scripts in an interactive way. So it's easy, right? So if you just go here, you just read the documentation. Traditional code is, for example, we do this logic here. Then we can run this cell, and we know the code that is going to do a statement, and we're just going to run that risk for cancer. And we can run these examples, right? We can run this person's going to be 55, 65, and we can run that, and yes, it does its job. But of course, this doesn't scale because there are so many. There are hundreds of parameters here, and there's a lot of variation, right? So imagine having to maintain this code. Is really not fair. It's not friendly. So what we want to do is constantly, as new data shows up, remember, so with time, things change, people change, the food changes, everything. So there's new things coming up, or maybe the numbers vary, right? So, and what I mean is maybe people before used to be 60, then 50. Now maybe people over 40 higher risk for heart disease because of what's happening in today's diets and so on, right? But with machine learning, we can change that by actually generating, creating a quick model. And this is very simple model, right? This is it just shows you the starting point, but it gets deeper than this. Okay, so it's a simple way for you to look at it and understand, okay, this is what we're going to do. So here quickly, I'm just going to create a data set, generate heart disease data. It's just really purpose is to generate some random data with age, overweight, diabetes, and things like that, right? And with that, and create a data set for that for us, right? So if we run this, you can see that the data set has 100 people and with different conditions, and with the flag called heart disease, yes or no. And this is key, right? Heart disease, yes or no. Keep into look at that one and understand that I'm giving you this information ahead of time because I'm going to dive into the details of what I'm saying right now in the next few minutes. Okay, think about that. So what we have here is what's called a label data set, right? So what we know is that we have a yes or no condition for heart disease. So if we're training a model to understand that, we can feed this data, and the model will look at all these parameters. And this is a small data set, but in reality, there are thousands of columns for this, right? But what we can do now is we can run this model. So if you use Python, you can use the sklearn library. And this is really all about machine learning, about AI and building models and things like that. So you can read about that, but they have a powerful library that can just do a lot of models, different models. And what I mean by models is that there's a foundational models to be able to do things like regression, random forests, and things like that. So you build your models based on those foundational models, right? So here we just basically say, let's create a data frame. Let's split the data. And this is an important concept. And you believe me, I'll show you more about that in a minute. You split the data. I just want you to see this. You split the data into the X and the Y. And follow the naming convention also is key, right? Naming convention here is key. X and Y have meaning, and the meaning is basically just be able to say that the X is the training data, is the labels that we're reading, and Y is our target data, right? And then we just sort of split the data into training and test data. And the idea is that with machine learning, you have a big data set and you split the data so you can train the model with a certain amount of data. And then you're going to feed a test data set, and then you're going to be able to predict on that data set. But this is really very compacted model that we're building. Is based on the random forest classifier. What this means, this is a classification type model. Why is that a classification model? Because it has a target label of yes, classifying into whether the person has disease, yes or no. And it's a classification model, and I'll get deeper into that, believe me. So here we just do a test, right? We say, hey, just get a random record here, age 55, overweight, true, diabetic, true, and then you say, is the person risk for heart disease? They have a risk for heart disease, and the answer is yes. If we go on to like 25, let's say, even though the person is younger and so on. So let me run the cells. So I have not run the cells here. So you have to run every cell to define the models, right? So this is just defining this, and now we can basically run this, and it says no because the person is young, right? But over time, this can change, right? There could be conditions that could make this person, even though this person is 25, a person that would be in risk for heart disease because that person is overweight, is diabetic, and so on, right? So if we do 65, of course, that's a high risk person, because we know the data set. We hard coded the data set, but that's really not how in reality it works. So how does it really work? Okay. All right, so we know now the foundational concepts, right? That's how machine learning works, based on data, and it can be trained. Okay, so let's talk about now the concepts of what this is, right? So the type of models that we have something called supervised learning, right? And these models learn from data, from labeled data, right? This means that we are training the model with input features, which is the X, right? The categories, that's the X, and then the desired output target, Y. So what we're saying is, as you saw in that little example, we're looking at all these other columns in the data set to see if the person is potentially has a risk for heart disease, yes or no. Right. And basically the goal of building this model is to be able to learn from that data and understand and classify the results, right? So, but examples of supervised learning, for example, is regression. And regression is basically something that is predicting things like stock prices, house prices. So it's really looking at, for example, predict the price of a new vehicle or so on, right? It's looking at numbers. And then we have classification, which actually is predicting a category or a label, a class label, right? So in our case, we looked at if the person had a risk for heart disease, yes or no, or if it's an animal or so on, right? So as you can see here in the graph, basically in the slide, you can see the concept, right? We have data. So we created a data set, and we have labels, and the labels were, in our case, little example was heart disease, yes or no. We did that training, we split the data, we did that training, we created a model, and then we did the test data, right? In the test data, we actually put in the 55-year-old man and the 25-year-old man, and we predicted something. And that was a classification model. In this case, you can see that in this particular test, I'm doing a number 5 and a number 2. And my prediction is number 2 is found, is successful, but number 5 is not. So if you think about it, and if you follow this, then you will understand why is 5 not found. Isn't this machine learning smart enough? And the answer is because 5 was never fed as a label into this data set. It does not know what 5 really means. So even though we have all this hype about machine learning and all this understanding, we still need to understand that there is a process to feed that information to the model so we can understand what we're trying to achieve. All right, so we have also the unsupervised learning. So this model, this machine learning models learn differently, right? So they learn from unlabeled data. So in this case, that means is that we do not have a target label. So we don't know if the person is a 5 or a 2. We don't know if it's heart disease or no. So we just have input data, random data that could be a 4, a 2, a 3, or 4, right? So, and those are, and what the model's gonna do is gonna look at input features X without any output Y, right? So it doesn't know what to do, but what it will do is learn those patterns and structure and relationships of that data and group that data. So basically what it will do, it will actually create a cluster of the data that is similar to it and associate that relationship between them. So for example, if you look at the diagram here, we have a bunch of data. We do the training, and it created a cluster that says that the number 4s are alike, the number 1s are alike, they're similar, right? So when we do the test on that model and we feed it a 2 or we feed it a number 5, it will definitely predict and classify that number 2 as the 2s in that cluster. But number 5, it will also say, I don't know, because I never had any 5 on my data set, so I don't know what 5 is. So it will say unknown. I do not understand it. So understand that unsupervised is now we don't have a target label. It's really just trying to group the data in a way that can classify it, right? So for example, how is this useful? So for example, in association, we just discover relationships. So when we look at medicine, for example, and we see these hundreds of data points, a pattern will be that the patient who report fevers and is coughing also frequently has headache or muscle ache, right? So it will discover all these associations based on all this, on other labels, right? Other features. So you will be able to know, okay, I see. Usually this person then has COVID or has a flu, a mild flu, or has something more, right? So that's how a machine learning will be able to identify people based on symptoms, right? And you have the model examples, clustering and frequent pattern growth, k-means for clustering, and so on. And those are foundational models. So you will hear the word foundational, which are models already pre-built, so you can build and enhance your models upon them. All right, so a common problem with supervised learning, which is is one of the easiest ones to achieve, right? There's 2 common problem types, right? Which is really regression and classification. And you kind of understand now regression classification a little bit because you saw an example, right? So the idea here is that we're gonna try to do so. Ignore the top. The top is not the wrong. It's from the previous slide. So this did not get updated. But let me go ahead and so focus on the regression and classification. These are supervised learning problem types, right? So meaning is we're gonna have a challenge. Someone's gonna say to you, I need to have this data set. I need to use a model to predict something. So in regression, basically, which is we're predicting prices, temperature, stock prices, you're going to use a regression model. And what it's aiming at doing, basically, with regression is looking at, and if you look at the diagram, it's looking at numbers close to that line, right? So it's looking at predicting something that is very close to that line. So you'll get all these data points everywhere. So, but it will get closer to predict, it will have to get closer to that line. And the idea is if we give him parameters for a vehicle, for example, we'll be able to say, I have noticed that vehicles in this class for this brand, for this year, for this horsepower, they're closer to this target price. And that is what's closer to that line that you see for regression, right? For classification, then what we're looking at is a target with discrete values, right? So we're looking at values that are more like yes, no, bird, dog, cat, you know, some kind of group, some kind of class. So what is the classification model is going to do is going to try to identify those groups and separate them. So in this case, it would separate the greens from the red, or it would just tell you yes for heart disease or no for heart disease. So it's really looking for predicting those kind of categories. Okay, but how do we go about to do this, right? I show you a quick example of how we build this model. How do we, we run it, we split the data and all of that. And that was a very high level introduction of a simple model. But let's talk about something that how does it really work on a real production type model development, right? So you will hear the concept MLOps. Machine language operations, right? Similar to the concept of DevOps that we talk about for development. And if you know DevOps, it's all about building out the resources, building the code, pushing the code, and so on, right? So everything is out there. So the same concept apply for machine language models, right? We need to develop the model. So it has a process. There's a process-oriented approach to do this. The first thing, of course, like any project, we need to understand the problem statement. What are we looking to do, to build, to resolve, right? Then you need to do data collection. So like data engineering. So think data engineering tasks now are fully useful and practical for this purpose. So you collect data, right, from the data sources, from a database, from CSV, and so on. You put them into a data lake. You do all that work that is part of data engineering, right? And then you got to go and understand the data. So you go in what we call EDA, right? Exploratory data analysis, which is what we do in data engineering to be able to go and say, I need to look at the data. I need to understand the data dictionary, the schema, the fields that are there, understand what are the features, and features, remember, ML and machine language just means the columns, the fields that are categories, right, and or numbers, but that are not the target, right, not the target feature, which is what we're trying to identify and predict. But you go through the exploratory data analysis, you look at the data and do that. And then you do your data pre-processing, right? And data pre-processing is that process of eliminating outliers, removing null values, following naming convention and standards, like renaming columns and so on. So all of it is data engineering. And then you go to something called feature engineering. And this is now starts going into machine learning engineering and data engineering, right? It's kind of a in between, right? So it's a great area, because feature engineering, what really is the process for you to understand your data set, understand your fields, the columns that are available, understand what you're trying to predict, and then understand if those columns are meaningful, right? And what I mean by that is, for example, in certain models, for example, you may not care whether the person is, for example, if it's male or female, as an example, that category may not be relevant to the prediction that you're trying to do. Like, for example, let's say they're trying to do to predict something that it will take that variable, male or female, and it may not be relevant. But in a medical machine learning model, to predict heart disease, cancer, and all that, a male, female is very relevant, right? Because statistically, you will see variations on whether the person is male or female, so it is important. But for other things that you're trying to predict, those fields are not important. And I'm just giving you that example because it's simpler. But for example, if you go to a vehicle, now if you go to a model for predicting the price of a car, it may not matter whether the car is automatic or standard transmission. By looking at the model, if you fit in that feature, then the models, it doesn't impact the target variable. What that means is, by training data on those two columns, do not give the model enough information to be able to predict anything, right? So, and I'm just throwing that as an example, and you see that there is a process to identify that. But feature engineering goes into that, into identifying the columns, and do a little bit of machine learning analysis, part of the tooling for machine learning, to discover those concepts. And you'll see more in detail. You have all the code in the repo, so you'll understand deeper when you play with it. Data splitting. So we saw a little bit of data splitting there quickly, but that is really what you have: a data set of data, right? And it could be millions of rows, millions, because machine learning models require a lot of data to be able to train on. So what you got to split the data is, you got to split it in amounts that are sufficient for you to have training data. And what that means is enough information for the model to learn, to have a high accuracy at predicting results. So you need a lot of data. A little bit of data is not enough, okay, for a very good model. And then you need some of that data for validation and testing, right? And what does that mean? So for example, you train the model on an 80% of the data set, and you can use another 10% for testing, for your normal testing. And then once the model is ready to go, you use the other 10% for validating real cases, right? And making sure that whatever the model is doing, you can measure that it's actually, the accuracy is good, right? And there are tools for measuring accuracy, right? All this, remember, now this starts getting more into data science. Machine learning, language engineering is about data science now. Looking at statistics, looking at performance metrics, and so on. All right, so once you know the data and you split the data, the challenge is, yes, 3 data sets. So training, testing, validation, and don't forget even more, because as the model continues, you continue to feed it data and more data and more data. So yes, so it really depends on the case you're trying to do. So now the challenge is, now you're presented with these requirements and you need to figure out what to do, right? So that's where model selection comes in, right? So the model selection is how do I start this? How do I do this, right? Do I pick a regression model, a classification model, a deep learning model, and you start going into down that rabbit hole of trying to understand what is better for that model. So that's really where it starts getting a little heavy now. You know, you need to have expertise. You need to understand clearly how we're going to do this and what model to use. So model selection is key. And usually what you want to do is you want to start having a 2, 3, 4, 5 models, select several models, train those models, and then evaluate those models, right? So, and then you will end up with a ranking of which one is best, and that's the one you're going to end up using. So the question is, you select 5, so we can't just select 1. You select 2, 3, 5, depending on what you're doing, and then you go to model training. And model training is that process of saying, I have my data split, I have my validation test set, I have my test set, and this is the data I'm going to train my model with. And you go through the process of training that model. And once you're ready to go, then you do the evaluation and model tuning, right? So, and the evaluation is really now you use your validation set and you start testing the model, right? And then based on those results, you can now do some analysis, some metrics, accuracy tests, and so on. So based on the model type, you're gonna have to run that, and that will give you, right? It will give you some kind of level of metrics where you say, yeah, these models do work, but this doesn't work. And if it's not enough, none of them are good enough, you need to understand why, and go back to model selection and try to figure out a different model, or try to figure out if there's something in the process that's not letting you perform. But the idea is, after you do that and you're satisfied with a particular model and it's performing well, and there's also tuning, by the way, but that's another deeper concept also. That there's different ways and strategies for tuning a model as well to improve it. Then there's concepts of overfeeding the model, meaning actually you're tuning it so much that you're actually making it sort of hard-coded on the decision making, which you don't want to do. So, but after you do that, then you go into deployment, right? And the deployment now, what the way you deploy this is really you're gonna deploy an asset, right? That is really packaging all this logic that we're talking about, and you're probably going to host it on some level of API somewhere where you can actually consume that. And when it gets an API request to say, "Can you predict this?" then go ahead and use this model and do it. Yes, yes, Fermin, yes, to prevent data leakage. That's correct. So, but okay, so we see that we sort of understand this. And there's a lot more concepts. Let's take a look at what is it that we're talking about. Okay. When you go to the project here, you want to go into projects. There's a projects folder, and then there'll be a vehicle MSRP, right? I have other projects there for heart disease, drug interaction. There are a lot more complex projects. So, but I think vehicle MSRP is very, very useful for us. So let's take a look at that. So you want to look at the regression Jupyter notebook, and I have it right here, right? So we're going to start with the problem statement, right? So the problem statement here is that we want to build a model that's going to help us do MSRP price prediction, basically, right? Utilizing our data set with attributes like make, model, year, engine, and so on, right? So that's what we're trying to do. Create a model that's going to allow us to create a vehicle price predictor, basically. And all these imports really are just, we're using pandas, numpy, which is for data engineering, and we're using the sklearn for the machine language process, right? So all these are the imports, and you'll see how we use it. So the first thing we do here is we prepare the data, right, and do the EDA, right? So just like any data engineering process, we look at the data, we're trying to make sense of it, right? We're looking at all the different fields and data points, and what are we looking to do, right? So what you will see here is that ultimately there is a MSRP column here. So immediately now, following our process, we understand, excuse me, let me go ahead and just forgot to. We understand right now that that this is a we have a target label, right? Because we're trying to predict MSRP, but we do have a target label, so we know we can actually go use that, and we also know it's a number, so we know it's kind of we can use a regression model for that, right? So that's the thinking process of what you do by analyzing the data and understanding it, right? So so you start doing data preparation, and this is just simple data preparation. It can get heavier as you, depending on what you're doing. Here we're just really replacing the names. We're making them lowercase because that's how we do it. That's the standards we follow, but everybody's different, right? We remove the null values. We rename the MSRP to price because that's how we feel doing it. These are just things that you do based on what you're trying to see, trying to find, right? So, but this just kind of covers the process of doing it. And then you just look at the data, understand it, verify, right? And then you start looking at, okay, let's find correlation here. Let's try to find the correlation of data points, you know? So basically what this means is every feature, every field in this data set relevant, meaning if you have 2 or 3 that are the same, like very close to being the same, then they're really not providing enough information, enough variation for you to feed the model, meaning they represent the same information almost, right? Basically, that's what that means. So what that means is if the vehicle, for example, a 2-door vehicle and a 4-door vehicle, they did not change too much in price, they probably are very correlated. They don't impact the price that much. That's the thinking process. So you can just kind of look at this code, that how it does the process, right? And then we just go and say, okay, let's get our numerical features and categorical features, right? Important because in machine learning, it really is optimized to run on numbers, binary data. So when you use categories like strings and so on, you're going to have to encode that data so it's easier for the process to work. Okay, and you will see this, how we kind of document this. So we separate numerical from categorical, and we identify the target label to be price, right? So we're setting up for this, right? So we're just kind of understanding now our data, and we're trying to find features that have the biggest correlation, right? So we run this process, and we identify we create a correlation matrix, right? That just shows every field in this data set, numerical fields in this data set, and see how they are correlated to each other. And we see that highway miles per gallon and city miles per gallon are highly correlated, right? So anything closer to a 1 is highly correlated. And what this usually means is that these 2 data points are the same, basically, right? They're providing almost the same information. They really don't impact the data much. The price much. So what you got to do is you got to make decisions on dropping one or making one out of the 2. So the strategy is you got to reduce the data set. The more data you have, the longer it's going to take to train and so on, right? So if you have a lot of fields that are the same, that are highly correlated, there's no point on training on that. So you probably have to make decisions of what's impactful or not. And in this case, we can drop either one of those, right? And now we can go ahead and just say what correlates to the price. So we can say, find the max correlation to the target price. And we can see that the engine horsepower correlates a lot with the price. It's 0.65, but that's the high correlation. And you can look at a correlation matrix, right, to kind of see what's going on and how they're correlated. And the darker the red is, then that's the highest correlation that you will have. And the idea here is that you're trying to minimize the number of features that you're using, because some of them are going to be redundant. And you don't need that. You just need one that's meaningful for the ones that are correlated, and use that, right? So this is what's called feature engineering, right? This is when you're going through this process of analyzing and picking up fields and determining what is useful. In our case, we're just dropping the city miles per gallon, and we're moving with a subset of categories. Be mindful here, because we are pressing for time. We can't really train the entire model on the entire data set, right? It takes some time to train a model depending on your data set. So we're gonna just select a few of them that we know are highly relevant, right? But the process is really to do the analysis, and you select the ones that are relevant. And we're just gonna train our model based on those features. So we select our features here, right? That's what we're gonna be working on. And we're gonna go into the process in the data. So we're gonna split. We're just gonna do 60, 20, 20 distribution here, right? And we're gonna get the training data, the training test data, and so on, right? And the target data and the target test data, right? So we're just splitting the data. And what we wanna do is, for our training data, remove the target label. So because the purpose of the training data is to understand how to arrive to a price. So we remove that column altogether. And then we can go ahead and look at our data set. And our data set now is that we have 9,531 records. Okay, that's what we're gonna train our model with. So we're gonna run another analysis, which is the mutual information score, right? And this is really to do analysis on categorical data as well. And this is all of that of trying to figure out what features are good or not, right? And for categorical data, meaning groups, then you do in one hot encoding, right? Because you're not processing strings, you're processing binary data, you're processing numbers, basically. That's the end goal here. And be very mindful here when you're training or not training to how you do your validation, your transformation of the data with the encoder, because you fit transform when you're training, and you only transform when you're going to validate the data. This is a common gotcha in development for machine language, but it's necessary, and you'll see as we get deeper. So, and we generate the mutual score. We run this. You can take a look at all this code later. And then once we run this, we can see the make and model have the highest scores for this, right? So you can see, so we understand make and model, and it makes sense, right? We sort of understand that it makes sense that these features are very relevant and important for prices, right? Because BMW is probably a lot more expensive than what is it called? A Nissan, for example, right? So, all right, so now we know that. So now we're gonna do model selection and training. I just follow this code here, where we do model training, feature encoding, right? And then we basically go ahead and decide what models to pick, right? So we're gonna start selecting, because we think it's useful, linear regression and random forest regressor, right? So we're gonna use those two, but usually you can use a lot more. And we're just gonna feed that data. We're gonna encode the features, right? Because we need to encode the categorical values. And we're gonna go ahead and run this, look at the shape of the data to make sure the fields are matching, and run the linear regression, and then fit the model, right? And that fit the model is really training the model to understand the data. And that's what really, depending on your data set can take a long time. And we do the same for the random forest regressor, right? We feed the data into the model and we fit it. Then we move on to do the prediction. So now we got to use our basically our validation, our test data, and make a prediction, right? We have to encode that data as well using the same encoder. And this is key too. You need to use the same encoder. Otherwise, the model will not understand if you use a different encoder. What that means even is an instant, not a type of encoder, but the instance of that encoder is very key, right? And then we go and we do run some predictions, right? So we use that encoded data, and it will just go ahead and run these models, and it will tell us that it found data and it's predicting. Linear is predicting 32,000, the other one's 33,000. And if you remember those charts, you're just following that regression linear a line chart and trying to match that line chart and spot those values there. That's basically what it's trying to do right there. And then we just move to model evaluation, right? And in the evaluation of the model, we're looking for some metrics. And these are the metrics that will tell us what the score is, right? And what you will see here is, and I have information on how to read this. Basically here, what we're looking at is that random forest has a better score at predicting, right? All the numbers here are much better for it. Not the best, but they're much better than linear regression. So we know linear regression is a no-go for us. So then what we do is we just chart the, we do a prediction versus a predicted versus actual, and we can see how we hit in the spot, close to it. So it's not so bad, but of course, always you find out if it meets your requirements. Now, this is the key. If you want to save the model, this is the process to do that. This basically will save the model into a file, which then you can use for your API calls, right? And you've saved those models, and then to load those models, let's say you're writing an API, this is the code basically that will go ahead and find those models, read them once they're deployed. Of course, remember you deploy it on an API, you will load those models, and then you will run a test, and then that test will execute and basically will predict the cost of that vehicle. And this is basically how you do the model development and deployment. All right, that was fast because we're running out of time. But so what we learned today is we learned about concepts, supervised learning, unsupervised learning, and things like that. So thank you. And I think, let's see. Yes, and we cover a lot today, guys. Definitely just take a look at that repo. I cover a lot of stuff fast, but there's more, right? If you go into the heart disease, yeah, you can deploy in an API. So API, you can deploy anywhere that you have an API. It could be a cloud, Azure, GCP. The concept is that once you have that library, you can load that as an asset into your API and then use it. If you want to use SQL Server, that's fine. But a lot of people, I'm in the philosophy that SQL Server is for databases purposes, not for other things, right? And I've been in companies where SQL Server is used for everything, which causes a lot of problems with SQL Server. But the concept is, how do you save it? How do you retrieve it? And how do you do that cycle? So basically now cloud companies, you can use fast API, you can use anything. You can do cloud functions, Lambda functions, anything, because it's just an asset. Think about it. It's just when you write your code, all you got to do is load it in memory and use it. That's basically how it is. So look at that code carefully at the last part of that Jupyter notebook, and you see how we just serializing that model into disk, and then we're reading from it and just using an API from it. So very straightforward. But so what happens is now you have the concept of ML Ops, and ML Ops will do all of this for you through a cloud turnkey solution that you can use. But I hope that I've given you enough just to get your mind and your questions flowing, be able to say, look, now I think I get it. Now I think I know how to get going and understand some of it, some of this stuff, but it gets deeper, right? So if you want to get deep into it, look at the heart disease exam project, and that's huge. That's a huge project right there. But anyways, guys, thank you for being here. Please follow the repo, guys. Follow that. Please start the repo. I need you guys to help me support that. If you're interested in that book, take a look at that book. I cover data engineering in deep concepts there. And wait for me. In a couple of days, I'll be sending all the resources, the presentation, and the video back to you guys. Thank you for being with me today. I appreciate your help and support. Everyone, have a good day.